Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 8, Projectivities in One-Dimensional Forms. Section 82, Parametric Representation of a Conic. Let a scale be established on a conic c² by choosing three distinct points of a conic as the fundamental points, say O equals 0, m equal infinity, a equal 1. Then, let us establish a system of non-homogeneous point coordinates in the plane of the conic as follows. Let the line OM be the x-axis, with O as the origin and m as infinity sub x. Figure 97. Let the tangents at O and m to the conic meet in a point N, and let the tangent ON be the y-axis with n as infinity sub y. Finally, let the point A be the point 1, 1, so that the line AN meets the x-axis in the point for which x equals 1, and AM meets the y-axis in the point for which y equals 1. Now let P equal lambda be any point on the conic. The coordinates x, y of P are determined by the intersections of the lines PN and PM with the x-axis and the y-axis respectively. We have at once the relation y equal lambda. Since the points 0, infinity, 1, lambda on the conic are perspective from M with points 0, infinity, 1, y on the y-axis. To determine x in terms of lambda, we note first that from the constructions given, any line through N meets the conic, if at all, in 2 points whose sum in the scale is 0. In particular, the points 1, -1 on the conic are collinear with N and the point 1 on the x-axis, and the points lambda, negative lambda on the conic are collinear with N and the point x on the x-axis. Since the latter point is also on the line joining 0 and infinity on the conic, the construction for multiplication on the conic shows that any line through the point x on the x-axis meets the conic, if at all, in 2 points whose product is constant, and hence equal to negative lambda squared. The line joining the point x on the x-axis to the point -1 on the conic therefore meets the conic again in the point lambda squared. But now we have 0, infinity, 1, lambda squared on the conic, perspective from the point -1 on the conic, with the points 0, infinity, 1, x on the x-axis. This gives the relation x equal to lambda squared. We may now readily express these relations in homogeneous form. If the triangle 0MN is taken as triangle of reference, 0n being x sub 1 equal to 0, OM being x sub 2 equals 0, and the point A being the point 1, 1, 1, we pass from the non-homogeneous to the homogeneous simply by placing x equal to x1 divided by x3, y equal x2 divided by x3. The points of the conic c² may then be represented by the relations 1. x1 is to x2 is to x3 as lambda squared is to lambda is to 1. This agrees with our preceding results since the elimination of lambda between these equations gives at once x sub 2 squared minus x sub 1 x sub 3 is equal to 0, which we have previously obtained as the equation of the conic. It is to be noted that the point M on the conic, which corresponds to the value lambda equal infinity, is exceptional in this equation. This exceptional character is readily removed by writing the parameter lambda homogeneously lambda equal lambda sub 1 colon lambda sub 2. Equations 1 then readily give Theorem 25. A conic may be represented analytically by the equations x sub 1 is to x sub 2 is to x sub 3 as lambda sub 1 squared is to lambda sub 1 lambda sub 2 is to lambda 2 squared. This is called a parametric representation of a conic. Exercises 1. Show the equation of the line joining 2 points lambda 1, lambda 2 on the conic 1 above is x1 minus the quantity lambda 1 plus lambda 2 x2 plus lambda 1 lambda 2 x3 equal to 0, and that the equation of the tangent to the conic at a point lambda 1 is x1 minus 2 lambda 1 x2 plus lambda 1 squared x3 equal 0. Dualize. 2. Show that any collineation leaving the conic 1 invariant is of the form lambda 1 prime is to lambda 2 prime is to lambda 3 prime as alpha squared x1 plus 2 alpha beta x2 plus beta squared x3 is to alpha gamma x1 plus the quantity alpha delta plus beta gamma x2 plus beta delta x3 is to gamma squared x1 plus 2 gamma delta x2 plus delta squared x3. Hint, use the parametric representation of the conic and let the projectivity generated on the conic by the collineation be lambda 1 prime equal alpha lambda 1 plus beta lambda 2. Lambda 2 prime equal gamma lambda 1 plus delta lambda 2.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.